So I'm happy to see a very full room. I'm happy to see that there's interest to this topic. Honestly, there are several parallel sessions that I would have chosen. but thanks for coming here. And there are some more people. Yeah, hello. Yeah. Come in, please. Yeah, I'm just starting. So this is a presentation about enabling computational computing throughout the virtualization stack. And the presentation itself will be all over the stack. It's not only technical parts, it's also putting things into context. Why computational computing and so on. So I assume if you come here, that means that you maybe know something or are interested in computational computing. But I'll also cover the basics and the motivations, like what is this about? What is this technology about? Why is it needed or not? So let's start with just a couple of words about me and Canary. So my personal background, I have spent many years in research up to 2020, and then I decided to move away from research and start a company to actually bring this into this technology into industry. And that's what I've been doing ever since with Canary. We're based in Sweden, and we're working on solutions for end-to-end data protection and secure digital infrastructure. That's it's a big sphere. And I have been working on computational computing and its precursors, trusted execution environments, since 2010. Working on TPMs, introducing TPM support in OpenStack. That's how I first got involved in OpenStack and started the OpenStack user group in Sweden in 2011. That was long ago. It's still running. So, overall, like, why computational computing? Today, workloads in use are at risk. So what does that mean? That means that when you submit your data to some service, well, very intuitively, the operator of that service has, in most cases, complete access to your data. What does that mean practically? So I can imagine many of you have used document signing services like DocuSign. Does anyone use DocuSign or similar? Yeah. Yes, cool. So 10 years ago, if I would be buying a house, that would be a contract between me, the seller of the house, and maybe in some countries there's a notary, in some countries it's not, depends. Today, it would be between me, the seller of the house, maybe some notary, and DocuSign, who has access to all the data, all the contracts, and will be running a lot of AI and machine learning, and as you can imagine, that's very interesting data. But that's just one trivial example. And there are many more cases where the data that is processed by some third party's software or service is actually quite sensitive, and you want to protect it. And in some other cases, it's not only the data, it's the software that is, maybe it's some proprietary code that processes data in some specific way. And that can be a business secret. And this becomes even more relevant in today's world where, let's say, AI is taking over the world, right? And data and proprietary business data, is the only thing that differentiates a business that is more or less successful from a commodity that can be copied and replicated very easily at scale with enough GPU power. So that's why protecting these workloads, and workloads in this talk will be both the data and the code. Just think about workloads. I don't want to differentiate here. And that's what computational computing tries to achieve, is to protect that throughout the life cycle. So, of course, encrypted at rest, of course, that's best practice. Of course, encrypted in transit, best practice, but also encrypted in use. So now, some of those who might know specifically the details of computational computing would say, no, it's actually not encrypted in use. It's in plain text in the CPU. Yes, it is true. However, if you consider the cost of an attack, and there are also attacks and limitations, I'll touch on them later as well on this. However, the whole point of this exercise is to increase the cost of an attack. Yes, there was a publication a couple of weeks ago with a €50, implant between the memory chip and the bus. You can, break this. Yes, however, that $50 implant needs to, be. You need to get to the data center and to bribe someone or hit someone with a stick and put that implant. That's quite difficult. That increases the cost of an attack. That's the whole point of cybersecurity in general, from my point of view. It's always about raising the bar. This is what confidential computing is about as well. Overall, what are the goals of it? Well, increase trustworthiness, raise trust. Trust is a decision. I see trust as a decision. I decide to trust a service. And this is a way to increase the trustworthiness of a service, of an infrastructure. Protect workloads and progress or use. That's what I was talking about. Expose a hardware root of trust. This is actually very interesting. This allows you to pin potentially a workload to a specific machine. You know that it's here. You know that it cannot be migrated from here. You know that it will only be provisioned to this machine, to this piece of hardware, if it fulfills certain policies that you decided upon. Facilitate platform security attestation. That's another very important aspect of confidential computing, is that it goes beyond just trust, but it goes to trust but verify. So it allows you to at least have some sort of a way to verify the environment where you want to deploy workloads based on hardware root of trust. And this hardware root of trust, it has very slightly different implementations between the platform vendors, but ultimately it includes some sort of secure element. And again, all the different platform vendors that implement this, Intel, AMD, Apple, ARM, they have their ways, their tweaks to do it, but it's always a secure element. And secure elements, they're everywhere. They're in all your credit cards, in your phones, SIM cards, and they've worked out pretty well so far. And finally, enabling attestation-based policies. That means that you can have a policy that says that I will only want to deploy a workload to a node. This node must be in, let's say, in group A, not in group B. It should be in the blue pool of nodes and not in the green ones. It should have a firmware version of a certain level, a certain firmware version, and so on. So it allows you to make quite complex policies, depending on which you will provision a workload, provision that workload with an identity, and so on and so forth. So that's, now I've been dragging a bit of time, but I think it's good to set up the basics. Now the evolution, just briefly, you could trace it like way down in 1999 when IBM, I think, did this secure coprocessor. It was even tamper evident. If you open it up, it would break. Then TPMs, then ARM Trust Zone. ARM Trust Zone was the first one that allowed, let's say, arbitrary computation, because TPMs, well, it had a preset number of algorithms or set of algorithms. Then TPM2 allowed crypto agility. You could update the algorithms and so on, but still it was like a fixed number. So Intel SGX, that was a process-based approach. It was good in many ways, but unfortunately it had also a lot of vulnerabilities. It also had terrible I/O performance, so it didn't really fly. So it's basically discontinued. And then AMD took a different approach. They started considering the entire virtual machine as a trusted execution environment. Yes, virtual machine has quite a large attack base, if you think about it. However, it's still a way forward. And so they moved that way, and eventually the entire industry moved that way to consider the entire virtual machine as a trusted execution environment. IBM, I don't know if anyone uses IBM, but they have this protected execution facility on open power. AMD, SCB, ARM CCA in 2021, Intel TDX as well. And NVIDIA, some of you probably saw this keynote from NVIDIA, there will be more probably. It was introduced in H100 and will be also introduced in their CPUs and so on. And the last thing, this TE device interface security protocol. This is the thing that excites me most, because this allows, this is a protocol that has been developed in the PCIe. This allows to create a kind of a confidential computing bubble between the CPU, the GPU, the SmartNICs, they all trust each other. Today you can do that between the CPU and the GPU through bounce buffers, bad performance, but you can do that. But in a couple of years, when the software support is there, then this will be possible to create this confidential bubble. Okay, adoption. We have a paradox here, that adoption wants to happen. We've talked to many companies, obviously that's in our interest. We're trying to commercialize this technology. They're interested, but they're asking like, so what about support? And their problems start. Software support is a bit behind, and tooling is a bit behind. Even the regulators are ahead. So this is, usually regulations are behind, but now they're ahead. This is a screenshot. It's translated from Swedish, where the Swedish Data Protection Authority, Personal Data Protection Authority, they have a regulatory sandbox where companies can apply to that sandbox to evaluate the use of a technology from a regulatory point of view. And there, down there, I highlighted, so the point of this, like we're doing this together with Ericsson and Volvo Trucks. Ericsson is a network equipment, a telecom equipment provider, and Volvo Trucks, Volvo Trucks. And in this example, we will be working with the regulators, or we are right now, to discuss how trusted execution environments can provide enough isolation from the underlying infrastructure so that the workloads can be processed in this trusted execution environment and considered to be as an extension of Volvo's domain. So it's like an extension of the truck. Because trucks today collect a lot of data, but they cannot process all of the data on the trucks. Anyway, regulators are interested. There was a similar sandbox in Singapore before, but the tooling is missing. And that's what we're going to talk about. Now, platform support. I will be missing some platforms. I'll be including some others. But what we're interested in is AMD, CD/SNP, Intel TDX, NVIDIA, and ARM/CCA. Maybe there are others. There are other architectures in other countries. They're out of scope today. So all of them, they have some sort of confidential computing support. All of them have some sort of attestation support. Now ARM/CCA, it's the hardware is not really there, or it's somewhere there. I don't know where. Some of them, they also have support for virtual GPMs. So a TPM, initially in that evolution slide, there was a point about the TPM. There was a chip that could be attached to the motherboard, a physical one, and the same specifications have been implemented to create virtual TPM. VM migration, it is supported. Well, supported and implemented are different things, but there is support. There are specifications for that in AMD and Intel and ARM. NVIDIA doesn't need that. Open source, I marked some stars because, of course, none of them are fully open source, but some of them are better at being open source or creating open source tooling and so on. So they go stars for me, and NVIDIA is slightly worse. Okay, so what else? Let's say we want to use confidential computing. So we chose a platform, depending on what we need. And now some of them will say like, okay, but we want to use a cloud provider, like a hyperscaler provider, because we like it. Well, among the three ones, again, there are many others out of scope. Let's just focus on this. Azure has gone kind of all in on this. They provide support for confidential VMs. They even provide support for some sort of confidential containers, not to be mixed up with the confidential containers from Kata. I think Azure will have their own, let's say, approach. Attestation service. So Azure has its own even attestation service that allows you to verify that their own deployment is secure, which is already a bit of a conflict of interest from my point of view. But, there are smart people working there, so they probably have their reasons. And then which platforms they support? They support AMD, Intel TDX on Azure and GCP, but not on AWS. AWS is mostly AMD, and then they have their own implementations. And then NVIDIA, confidential compute, so you can attach GPUs with confidential compute on Azure, and very recently on GCP. So that was added like just now, the end of August or September, very recently. Okay, so it seems like we can take this confidential compute. We're happy. We go to a cloud provider and let's say let's run and let's be secure. The problem is that there are also quite nosy academics, luckily, that also want to investigate this and then want to really dig in and see like, okay, so what is behind these claims and what can we really verify and trust and so on. Well, it seems that none of them are fully verified. But you always have to take a leap of trust. Leap of trust. Well, just before this talk, we were talking about one of these cloud providers, and then there's always this little black box binary that you just need to trust. And that's a bit of a problem here, because if the goal is to have, let's say, confidential compute, you want to protect your workloads in use, you pay a premium for it as well, both in performance and ultimately money as well. Then you want to, be really confident about it and be able to show it to the regulators. Like next week, I'll be talking to this Swedish Data Protection Authority. They are very technical people, and I will need to convince them about how this is done. And I cannot convince them if there's like, well, you just need to trust this binary from Azure. That's not going to fly. And the link to the study is there in the source, very small font. There was another study that built on this. It was the same. It's about what can also be attested. So the attestation is it's a protocol where you, let's say, compare what you get with what you expect. And to know what to expect, you need to be able to kind of pre-calculate that. And so again, you're not always able to pre-calculate the expected measurements because you don't know how they are implemented. And that is a problem for basically all of them. So it's quite patchy. Ideally we want to have all those circles black, but they're not. And this is where, again, you need to start having a leap of trust if you want to use the hyperscalers. And that's what we don't want to do, especially in a day and age when the hyperscaler might decide to just turn off your service if they don't like it, for certain reasons. So, my statement here, why are we talking about this here, enough of the hyperscalers, is that transparency in the verifiability is a core advantage that open infrastructure can offer to confidential computing. And that's where it really is different. It's hard to compete with them on features. They're ahead, that's true, let's acknowledge it. They're good, yes, we need to also be good and better. But transparency and verifiability is a core advantage. How can we use it? So now let's say we ditch the hyperscalers, let's do it on our own. What do we need to do it on our own? We need to first have support in the host kernel, KEMU, live there, and guest kernel. So make a distinction here. Host kernel runs on the host, and the guest kernel is the kernel that runs in this confidential VM. Both need to have support. It's different types of support, but both need to have support. Luckily, this support exists. So the guest kernel support was there early on, both for AMD CDSMP and Intel TDX. And that's when the hyperscalers started marketing like, yay, you can run confidential VMs. It was completely unverifiable, but they claimed. Now, host kernel support was added fairly recently, 6.11, and we can imagine the timeline. And then, based on that, the support in KEMU was added and in libvirt. So, in this race between two horses, AMD is slightly ahead, or was slightly ahead. Intel TDX was slightly behind, but now there's a parity there. So there's the virtualization layer support. If you want to do it completely on your own, just run with KEMU and libvirt, it can be done. Most people would prefer to use some sort of virtualization manager. Most companies, they don't want to run scripts with KEMU. Now, looking at enterprise virtualization management, of course, there are names that are not liked here, VMware. Unfortunately, the reality is that many companies are using them. So let's face it. And they did have support. They added support fairly recently. Their roadmap is always a black box. Nobody knows, but they did add it. Citrix, they don't have anything. Hyper-V, they added that since their 2022 Windows Server something edition, but only for Linux. So Windows is out of the scope. Proxmox. So Proxmox is an open source virtualization manager based in Europe, somewhere, I think Austria. One of the customers that wanted to do this and didn't want to do it with Kemu and with Virt said like, okay, so what about Proxmox? Does it support it? So we started looking into it. No, but wait a bit, maybe it can. And so last year we started looking into it and added support for AMD, SCD, Now, this work in progress, we're adding support for Intel TDX. Why we chose Proxmox? Because, well, first of all, there was a customer request, and second, it's smaller projects. There were not many discussions. We sent the patches, they liked it, we discussed a bit more back and forth, they accepted them. That's it. There's no need to convince someone. So that's an important part, and support someone. Yeah? A word on performance before we go a bit deeper into what we added, how we added, and so on. So performance. Some might be interested in performance. It depends. Yeah, as with any performance benchmarks, you cannot say that some platform has performance X, Y, Z, right? It depends what you're running, how you're running, and so on. There are several good publications that measure performance overhead of TDX and SCD in great detail, and I would rather trust them than the vendors, of course, because the vendors might be sugar-coated. We had our own study of HPC-specific benchmarks. In that case, we had access to an SCD platform, so that's what we studied. We're trying to get a fat enough Intel platform with TDX support to run HPC-specific benchmarks. But it was a master thesis, very well written, and it's in great detail. And but most important also that there are many improvements on the way that will further cut down this performance over. And since then, everyone I see with a badge of like HPC, I'm asking them, okay, do you care about security? And what's the trade-off? So if anyone is working with HPC, I would like to talk to you. Okay, so I mentioned that we added this contribution to Proxmox, so this is a bit of an overview. Okay, how are we moving towards this? We added Proxmox in support for AMD SCD in version 8.4 that was released in April this year. And the next release, if everything goes according to plan, and the next release there will be a combinational computing support with remote attestation for Intel TDX. But already today you can get Proxmox, get a machine that supports AMD SCD, anything that was released after 2020, and you'll be able to try it out. However, again, if you want to run it at some sort of scale, you don't want to run manual scripts, and we have a orchestrator to deploy these virtual machines. It's based on OpenTofu, Terraform OpenTofu, as a module. It's open source Apache 2.0 license for the hyperscalers. We keep it for now proprietary for the on-prem deployments. And this work was nicely supported by research activities in which we are active. So Local Flex, that's a project with a bunch of energy companies, including EDF here, that is located very close here, that is developing energy flexibility markets. That's quite sensitive data. That's where we're adding support for computational computing. And Titan, European Open Science Cloud, this is again for support for, let's say, research data, but in some cases research data might need additional security. So there you go, computational computing has a use case there too. Right, so now let's go a bit deeper about how difficult was it. It was not difficult. There was some work, but it was not difficult. We did it around December, March 25, December 24, March 25. So we needed to change the OVMF build target for S&P. I must also mention that it was slightly easier for S&P, that's why we started with it, because Proxmox already had support for the kind of the previous versions in DSCV and in DSCES. So we just built on that. So once part of the stack is already adopted, that's already easy. Then kernel 6.11, was there in place. And one showstopper that apparently, I didn't expect was that, those guys said like, yes, but we don't have hardware to test it. So we managed to fix that. And then it was released in the version 8.4 in April 25. Now, as I mentioned, we're adding support for TDX. Again, we need a slightly different OVMF build target for TDX firmware. There's one kind of issue about how Intel does things, that this build target didn't include the SCSI driver, which is the default storage driver for Proxmox, but we made a workaround to include it manually. Otherwise, the process is that whoever wants to use it, like Proxmox, would have to make a request to Intel to say, like, consider including this by default and so on, but that would take many months, and we don't have that. There was some bug where boot time took many minutes, and we were scratching our heads what the hell is happening, but that was a bug caused by Kevin. Now it's fine. Of course, some updates to the graphical interface that Proxmox had. Some backend updates, because first we added support for AMD, SVSMP, and even if you assume there will be other technologies, of course, sometimes like things are called or named or shaped for the first time. And then, yes, mapping PDX. Okay, additional work. So Proxmox is based on Debian. So we had to dance around that. Mainly it was about hosting configurations. Again, kernel versioning. Proxmox by default at that time currently uses 6.14, kernel 6.14, but the host support for TDX is in 6.16, so we need to patch that. And then also we were waiting for the for Canada 10.1. Now it's there, and of course Proxmox had their own patches to Canada, and then they took care of that. So it was, of course, a teamwork as well. Orchestration. So as I mentioned already, this is a precondition if you want to have correct deployments at scale. You can do deployments and consider that they are computational computing, but if it's not well configured, if it's not correctly configured, then you're lying to yourself. And that's why we have this OpenTOEFL-based module for deployment at scale. It supports basically that matrix, what I showed you, like the hyperscalers for AMD, SVSMP, and Intel TDX, and also the on-prem solutions. Okay, and of course now we're at the Open Infra Summit, so let's talk about what's the state of the art in supporting computational computing in Open Infra. So, Kata containers, great project, we love it. This is really I truly love this project, and we're going to use it in many different use cases, situations, and so on. There are many other presentations today and tomorrow, and they will be much better than what I can tell about that. OpenStack. This is the reason why I came here in the first place, why I submitted the talk, is that OpenStack was, quite ahead. They added, support for ACD, AMD ACD, which was the state of technology in 2019, and they added it directly, which was good. The trajectory was good, but then nothing happened for 6 years. I don't know why. What I heard is that the contributor, the company contributing to that, they left OpenStack and they're not contributing to OpenStack, and then no one else took this decision. Now things are moving very slowly. SCBS support was added in Nova like this year. This is good, but it's definitely not enough, because if we are to say that, yeah, we're going to take over the customers from VMware and move them to OpenStack, well, some customers, they're not only going for the cheaper solution, they're also going for the features. And in this case, the features are really missing. And yes, computational computing is not like everyone in the street is shouting for it, but there are high, how should I put it, critical infrastructure and other domains that really need it. And they're really ready to pay for it. And they would be willing to use OpenStack, but it's missing. So, yeah. I think this is how I would like to add it. to end this, it's time to add confidential computing support in Noma, support for SVSMP and TDX. We're a very small company. We're really willing to work with together who wants to help out and do it. We don't really have the muscle to push it to OpenStack. But this is my call to action. So whoever is interested, let's work together. Thank you.